Tonight we're going to go over Team 581, the Blazing Bulldogs CAD of their 2025 in-season rebuild. So they should have the CAD and GitHub links and everything on Chief. And they had an original robot that then they modified before the championship to build out into what ended up being a pretty common rebuild design. Them, 8044, a couple other teams built to something similar that's a little bit of several other robots that are all combined. So Chill Out had a robot that was similar to this. The intake on 5D1's robot is similar-ish to 1323. And some of the others like that. Then the actual coral placement and things are similar to how 2056 and several of the other ARM robots, Orbits of the World, all of those style robots sort of place. So we're going to look through their CAD and kind of see what we can find of how they designed and built this robot, and what we can learn from it. Okay, so we're just going to go through their public Onshape. I think everything in this kind of moves around, so we can get a good idea of how the robot actually works, starts, everything like that, if we can get into a good space. Like normal, we can start splitting the robots up into their respective mechanisms. So this one has voice. Okay, I think this is okay. All right. If my mic quality is bad, I'm getting a notification somewhere. But I think we should be okay. Oh, maybe not. Now it's doing other things. Okay, hopefully that works out throughout the rest of this. I'm on my backup microphone. But the normal subsystems or mechanisms for robots in this game are all pretty standard-ish. We're going to have our drivetrain. We're going to have some kind of intake. Sometimes it's combined with the scoring mechanism. In this case, they're separate, so they have that handoff. We're going to have an elevator, then the arm, then the manipulator or other intake, whatever you want to call it. This intakes algae, grabs the coral from the ground intake. And then they have their climber over on the back. Yeah, so here we have drive, climb, coral intake, elevator. They call it the claw and arm. They have their carriage separate from the elevator entirely, so that makes some sense. It's a lot more integrated than the rest of the elevator needs to be. So it's definitely a little bit of a different design work. And then they have their bumpers as well. All right, so let's go ahead and look at Drivetrain real fast. This can be quick. They're all pretty much the same nowadays. So they're running the West Coast modules, inverted, relatively normal stuff, 2x1 going across them. And then we have some amount of a belly pan, a little bit of a double belly pan, it looks like. So they have some extra either weight there or mounting there. Yeah, so it does seem like it has a few more holes that they may have needed. They're also just mounting their elevator straight into this, so that they may want to do that just to stiffen it up to avoid putting it just on the relatively thin standard belly pan, which is 0.09. So they added another probably 0.09. Oh no, a whole eighth there. So yeah, so they added a bit of stiffness coming back here to allow for that elevator mounting and to get those holes in the right place. So it's very possible that this was the belly pan of the original robot, and if you had to move your elevator, if you had to move other things, and you need to be able to set those holes. They did have it seems like they have the elevator post holes here already in CAD, so I don't know exactly what they're adding, but they added some holes for the rest of the mounting as well, and even just to stiffen it up. But that does seem a little bit unique there. The rest of it, like I said, seems pretty standard sort of modules. They have some little riser pieces for their belly pan protectors to get that up off the ground a little bit. You can see a couple others in there, just to make sure they had place where the coral can't get caught down there and to make it to where they're holding multiple game pieces. And then we do see their camera mounts on top of the swerve. They built in some things to be able to have adjustability there so they could change the angle of where these were mounted without having to reprint these camera mounts that are all 3D printed, I assume. Let's see, anything else in Drivetrain? Doesn't look like it. Looks pretty standard. We can check out their bumpers real fast. Looks like they have some 2x1 just screwed into the back of the bumper, doing a full wrap, all four sides is one thing, and then putting it over the top. We can see that together a little bit. Yeah, and so these just come down and have places to bolt in on top of their chassis rail. And so they're just bolting in that way, and then I think it looks like they have to like possibly move part of that cover or just kind of slide it around it to be able to get in there and bolt those in. Not a bad way to do it. Seems pretty easy. You get a captive fastener, so you don't have to have the nut on the other end. Let's see, so if we hide the bumpers, we can kind of see how they made these plates. So yeah, so they have these plates here that get probably countersink rivets into there. And then on the underside, they have, these are pressed in PEM nuts. So they're specifically designed to be pressed into sheet metal. So they didn't just like capture a nut pocket, they just made the hole. Then they press in these hex PEMs, which you can probably see. Yeah, so there's these flush mount press fit nuts for sheet metal. Probably, yeah, they can just get them on a master. That looks like a master part number. So something like that would work pretty well. It lets us just bolt in and out from the top here. Don't have to worry about those. And if you do need to replace them, you can just drill out the rivets, pop in another one of these. If somehow you cross thread the nuts or something, or if you damage something, you can get back to working pretty quickly, and you have a second bolt on each one, so you're almost certainly not cross-threading both of these each time. You could run matches with only one on a side or something if you needed to. All right, let's move up from drivetrain and bumpers. We can go to intake next. Actually, we can go down in order. We can go to climber. So that's climber side of the chassis. Let's go to actual climber here. Okay, so climber is mounted across their swerve modules actually, so it doesn't look like, because they had to like keep room for their bumpers blocks to come in and meet down here on this lower chassis rail, they actually made plates that just fully mounted to their swerve modules. So they have standoffs coming up from the swerve module bolts here, and then bolted into the swerve module plates. And so they're getting a lot of structure directly off their swerve modules. Would definitely be a little bit annoying if you had to swap the modules for some reason with how much they integrate into the corners. But also you don't really have to do that much anymore. Like the swerves are so much more robust than they were years ago before they became COTS and everybody understood how to build them better. Like we haven't had to take a swerve module fully off the robot in a while. So you don't have to do it very often. Most of the stuff you could still get to if you needed to. Pulling the camera off or even pulling one of these plates off wouldn't be too bad if you needed to be able to swap out the module or get in there to repair it for some reason. And then it's just the 1x1 going across 1/8 inch walls because you are supporting the whole robot off this when you go to climb. So it's probably worth the weight over a 1/16. And then they frame it back to the chassis in a couple ways. They have this arm here that comes down to a nut strip on the belly pan, so they don't have to have a whole crossbar or anything on their belly pan. They have a pretty open belly pan where they're not putting any crossbars across actually. So it's just the 0.09 thick aluminum the whole way with no crossbars except for like this, the little one here, kind of mostly just for protection. It's not doing a whole lot of stability there. But they are still able to tie into it and get some support with a nut strip here and then a big piece of trussed out aluminum up to this bar on one side, and then they have the spacers and everything connecting it to that main pivot plate as well. So they're supporting the main pivot plate and the actual tube structure they have for the actual climb here. And then on the same side, it comes over and gets supported into the elevator rail. So that prevents any like leaning or twisting on this, or helps prevent quite a bit of that. So that makes it quite a bit more stable when you get those extra points of contact out and you're not just mounting it on this one rail here. So that definitely helps it. Okay. These basic versions of these climbs all kind of work the same way. They have one motor up here that powers the wheels that helps pull in one of the bars of the cages. So these wheels kind of grab the bar and get it sucked in and like completely compress. So these are compliant wheels, and the bar will completely compress and get lodged into this curved cutout right here. So this is like the size of the cage bar. And then below it, everyone has some slightly different ways for how they actually latch the bar closed. I'm not entirely sure how they do it. Let's see if there's anything. Yeah, this is probably hard to find in CAD. There's almost certainly a spring somewhere here that allows these to move in some way and stop the bar from coming back in. So most likely these are kind of sprung back this way. So that as the bar comes in, they get pushed out of the way. And then once the bar passes them, they come back again and get in front of the bar and just don't let it leave without having these pulled back out against their springs. And so that latches the bar into place. That's my guess at what's happening there. Some version of that is how most people's works. This is a pretty simple one because you just need the springs. You don't have to have any other sort of latching or positive latching mechanism at all to do anything else. Below that, you actually have to then tilt the whole mechanism back to get it to actually climb the cage. So once the bar's here, the goal is to kind of bring the chain down and in towards your belly pan, get it right above your center of gravity, so that the robot's kind of level and not touching the ground on any corner. And so to do that, they have this whole thing mounted on a hex shaft. So this is just a normal 1/2-inch hex shaft, it looks like. Yeah, nothing too weird there. They're supporting it pretty close, so this gap is not very long, so they don't have like a really big span where you'd start to worry too much about the hex shaft trying to bend and become a lot harder to actually do your climb on. If you have a smaller diameter tube or shaft that you're trying to lift the whole robot weight on or trying to put a lot of load on, you really just want to be supporting it as close as you can to where the load is, and that stops a lot of that bending. So even if you can have fewer space here, if you can like tighten this space up, it'll reduce the bending even more. At some point, it's good enough. This was working, so it's probably good enough. They do have an encoder, so this is a Vex through-bore CAN encoder adapter. We used these briefly last year on our launcher to get angle, and then we swapped to the new through-bore encoders, but they all do the same thing. There's just a CAN encoder goes here. There's a little gear train inside here to give you the exact rotation of this shaft so they can know how far they've deployed and how far they've retracted. And then to actually do the retraction, they just have a Kraken into a Max Planetary and another hex shaft here. And so it's likely that there's a string tied somewhere into this, and it's just spooling along the hex shaft. And so as it winds up, this gets pulled back and they can do the climb. and there's some way to release it as well at the beginning of the match, most likely. I don't know what they're doing for the release, but it's probably sprung forward somehow, so that as this releases and as the string is unwound, this is getting pulled forward, and then as they wind it, they pull it back. And then to hold after the match, this little block right here should be the ratchet plate. So this is a West Coast Products product you can buy that basically just has a ratcheting wrench inside of this little block. And so just like the way one of our normal box end ratcheting wrenches works, there's a little gear teeth and a little prowl in here, so it only lets it rotate one direction. And so then after the match, when they want to reset it, they probably have to unbolt this to be able to spin the shaft the other way and then bolt it back into place. That's my guess at how they reset it. They could be doing it some other way, but it's probably something like that. You could also just like you could take the shaft collar off and pull this off the shaft. There's a lot of different ways to do it. If you use a normal wrench here, you can kind of like, or if you have one that has like the reversing action, you can pull tension off it and then reverse it, let it unwind, and then flip it back the correct direction before every match. We've done that before. That's how we do it in some of our rope tensioning or belt tensioning mechanisms for our elevator. They all kind of do the same thing, just different ways to use a ratchet to do this same style mechanism. Yeah, so nothing too crazy for climb. Moving on to the coral intake. Let's see what we can see here. So you can definitely see some inspiration from 1323. They have kind of similar kind of wedge action going on, dual rollers. It just sort of picks the coral up, holds it between this roller and these ones. It'll do some self-centering, so it'll center like between these plates or so, or at least it should. Just as the coral's kind of at an angle as it's driving through, it'll kind of center the same way our claw does on our robot. And it'll kind of spiral in a little bit until it gets lined up on one of these two edges or between those edges. Let's see. So how do they do deploy and power? So power is relatively simple here. So we have a Kraken X44 driving a small gear that's then just driving a pulley out to this front roller. So just a belt, so then the Kraken moves with the whole intake when it moves in and out. And then on this side, you get this shaft getting powered, and then you have your reversing gears right here that drop down to another pulley to power their lower roller. So that it's going the opposite direction, so when this is spinning in, this one's also spinning in the other way. Let's see. So yeah, they did do. So they have their bearing flanges here, and they have little plate to kind of hold the bearings in. So this little sheet metal plate is bolted across the top of those, and so this stops those bearings from wanting to pop out at all. And it also stops this plate from wanting to like flex away and leave the bearings and shaft just on the shaft, so it kind of holds everything together. If you don't do something like this, you can sometimes get flex enough to where the bearings will just like pop out, and then everything's not aligned where it should be, and then the whole intake just kind of breaks and doesn't work right. This shaft, because you only have, it's not going all the way across, that would just be more weight. They have a couple standoffs here just to have your other bearing on the other side, and then it looks like they just have the shaft collar here on the inside, and with everything being spaced correctly, this shaft can't come out as long as this shaft collar's tight, so you don't have to have snap rings or bolts or anything on the ends of these if you just have the shaft collar inside. You could also still, if you want more reliability, have these tapped or snap rings cut and hold the shaft in that way. That also works. They're using shaft collars here, but you could do the same thing. You could cut snap ring grooves, you could drill and tap the shafts, or if you're using rounded hex, they could already be tapped, or they already have the hole for it. You can just tap them. You don't have to actually drill them. Kind of same thing going on the bottom. yeah, these plates just kind of stop the coral from wanting to be into the belt or anything like that. So you get a little bit of help there and get some of that centering effect going on, and just stop the coral from like going too close to the sides of your tube or anything like that. Um, and these back bars just stop the coral from going too far out, like going too far in, and actually getting it stopped in a place where you can still eject it back for the handoff or for potentially L1 scoring. Um, okay, the other part of the intake is how they actually pivot it. And so they do that with these large, what are called sector gears, because they're just a portion of a full gear. So it's some percentage of a full gear. They don't need the whole wrap because they're not moving a full rotation. They're just moving part of a rotation. So they can design it specifically for how much rotation they want. And so you can kind of see where the gears kind of end up. So you still have a little bit more. So they can go somewhere like that. That's about where CAD stops it. And you don't see any like mismeshing or anything. You don't want to go too much further than that as you start potentially missing a tooth or something there. And then that's just driven here by a 10 DP. So that's why these gear teeth are large. These are like twice the size of our sort of standard FRC gear teeth that you can see like over back here on the swerve modules. These are 20 DP. This 10 DP is a lot easier to cut, so you can cut this profile on a CNC router a lot easier than you could potentially cut the 20 DP. You would need a really small tool to cut 20 DP gears. It's also really easy if you can get them laser cut. So something like FabWorks, they can cut these 10 DP gears pretty easily. Them being aluminum, the gear teeth are just a lot stronger because they're bigger, so they have more material there, so it's harder to break off a gear tooth than it is on the smaller gear teeth. So a lot of times we'll run steel for our small 20 DP gears, just so the teeth are strong enough. You don't have to worry about that with the 10 DP. We did run steel side plates, but we like reinforced ours with steel last year just to be extra sure as we were running through the. We used it for our launcher pivot. But you can get away with aluminum here without too much of a problem. The rest of this is just a pretty standard gearbox, Kraken, pinion into a couple gear sets. The gears aren't fully modeled, they just model them here as their diameters, but it works well enough for what you need in CAD. And then kind of all that same sort of driving, and you have the jack shaft here going across, so you get the pivot powered on both sides. They do widen it a bit with a big 3D printed block, so they can bolt all the way through that block and get a little bit more width for their intake without moving the gears further out, because you can't really do that with the way the swerve modules are. So you still get that room there. And then they do have a little bit more going on, so they mount the limelight off a plate off this intake, just because that's where they needed the limelight to be on that side. And so they can make a quick little plate there and some 3D printed stuff, because that whole thing is 3D printed, to get the exact place they needed for that. And then they do support the end of where the intake pivots, since they are like overhanging this so far. They support that farther out with these small plates that are just on nut strips off of their swerve modules. And so they have that on both sides. So this long tube can be supported on both ends. It's not going to flex or anything. You're not just fully cantilevering your intake off these inner plates. But this doesn't have to do much more than just like kind of keep everything straight. The other nice thing they did that we can kind of see here is this tube is captured sort of by these two different plates. So it's not running through a hole in this plate, because then installing it gets really annoying. You'd have to like slide everything through nicely each time you want to install it. So if you wanted to take this intake off, if something happens to it and you need to replace it, you'd have to like pull this tube out, get the next thing ready, put everything in an order to slide it all through. And that just takes a long time. It's a process that's easy to mess up. And so instead of that, they have this like double capture plate here. So instead of having like a circle, they have two half circles. Let me see if we can make that easier to see. Let's see. There we go. So they have this first, oh, except I blocked it immediately. All right, there we go. So now we have this first half circle below it, and then the one on top of it here is the other half circle. So then if you unbolt this plate and you do the same thing with the plate on the other side, and you unbolt the shaft ends from out here, this whole assembly can just be picked up by this bar, taken out, a new one can be put in. You can swap your motor wires, whatever you need to do, and you can have a whole intake swap in 6 bolts and a few wires, depending on how your wire harness works for your Kraken here. So you can swap the intake really fast if something were to happen. Where if you had just put this through a hole, it's a lot trickier to do and a lot more work. So something like this helps a lot with maintenance, being able to just capture that shaft. Since this shaft itself doesn't rotate, because the intake's spinning on its own bearings here, right? So it's on half-inch bearings. So it's just spinning around a shaft that doesn't rotate. You don't need to worry about having bearings in this plate or anything. You're just trying to hold it all center. So something like that works pretty well. This same thing could be done with a half-inch hex shaft. It doesn't need to be round. You would just use hex bearings here instead. And then you could have either a hex cutout hole, or with the rounded hex, you would just have the same profile, the diameter of what a rounded hex bearing is in here, and it would work too. Okay. As we move on, we can move over to their elevator. I'm going to isolate for that so we can get a little bit closer look. Okay. So I'm just going to hide their like back sponsor and protection panels. So we're not seeing that. We can kind of see why their elevator is a little different. So this elevator is a what we call a cascade elevator. So instead of having a continuous string or a continuous belt going all the way from the bottom up to the carriage and like pulling on the carriage directly, they're going to like move one stage at a time. This is similar when we looked at like 2910's extension, that was also cascade. So similar concept to that. And so the powertrain for the elevator is back here. You have your 2 Krakens driving these 2 gearboxes with a shaft that connects them. So you're getting the same amount of power to both sides. If you didn't have this shaft and you had each one powered, it'd be very easy for like one side to get a little bit faster than the other. Then the whole elevator's kind of trying to go up crooked, things you don't want. So always having the connecting jack shaft is very helpful. It's all kind of mounted just with these like nut strips coming off the 2x1, and then going out, and I think they have a nut strip going down to the belly pan. So this is definitely a convenient way to do some things instead of having to have like cross members and everywhere having more like 1x1 or anything. Just having the mounting that you need into the belly pan definitely lightens things up a little bit. While we're here, because I forget, we can see like they have some mounts here to get this angle. These are just like 3D printed. Or you wouldn't quite be able to, you wouldn't get the same shape any other easy way. They're running some bolts down it, which is interesting. So yeah, so they're running bolts down through the print. And you can tell it's like it's not actually printing, it's not actually bolting anything, right? There's nothing that this is attaching to. The bolt ends here stop before the stop before they actually mount to anything. And so what we can kind of surmise from that is that these bolts are just there to reinforce the plastic here. So if you have any sort of like layer defect or something during the printing process, you might have a weak spot. But if you have the bolt running all the way through it, it's near impossible just to like snap off any part of this print, right? Like you wouldn't be able to easily just have this whole part of the upper part of this print just break off, because you have that bolt reinforcing that whole length there, helping make that whole thing stronger. For a pretty small amount of weight, you can make a piece of printed plastic a lot stronger with a simple bolt. Okay. Back to the elevator. So it's a relatively simple elevator, similar to what the Spectrum 2024 robot did for our amp trap. It just has the two chain paths that allow that first stage to be lifted up and down. Um, so you have this block here that's going to have some way to bolt through the chain, and then some way to be attached to this rail. Yeah, so you see they have the little plate here. So you're going to have number 440 bolts that kind of pass through this and let it all bolt together. This works. There's a lot of different ways to do the same thing. The Thrifty Bot elevator kit, and I think they sell them individually, has little specific things that are designed for this. I think we used them in 2024. They all do roughly the same thing. A couple of different vendors have elevator chain attachment block kit things, or you can make your own. But all it's really doing is making sure that as this chain goes up, this stage of the elevator goes up too. I don't actually think some of that, yeah, a lot of that motion isn't actually working here in CAD, but that's fine. So this would be all the way down at the bottom when the elevator's all the way down, and it'll go up as the chain goes up. For the top here, you see they put these plates inside, attaching to the inside of the 2x1 that then hold the top shaft for the chain and sprocket. So you can get some smooth movement there. And then they used I think these are the West Coast Products blocks. And so they have, whatever this is a 1/2 inch. Yeah, so they have a full 1/2 inch between their stationary stage and the first moving stage. That lets them have enough room to be able to do things like put this block here. But yeah, standard COTS bearing blocks here, so nothing too out of the ordinary. And they should have something similar down at the bottom. Yeah, so they use the different kind. So they use the kind of the inline mounting blocks. So these get mounted on the interface and have their bearings in here. So these are the same ones I think we used in 2024 as well. So they like kind of combine two different ones just for whichever need they had at the moment. They could probably have done a pretty similar one and just had that one at the top too. They may have had a reason for wanting to go the other way. I don't entirely know. But as long as the spacings line up, you wouldn't want to use a block that thinks you have a 1/4 inch spacing when you really need a 1/2 inch. That would make things a mess. But as long as you're like the spacing between the tubes are the same, you can pretty much interchange blocks on your up or down and not cause any issues. Let's see, what other parts of the elevator? So the actual carriage part and how they're able to move that second stage is with this string out in front. So similar to the string that was on the 2910 elevator or extending arm that we looked at last week. Here we have another pulley setup. So I think this is all a printed part. I'd assume, let me get back into there where we can isolate just that. Yeah, so that definitely looks like a printed part. So that whole printed block is going to go inside the 2x1. And then they're going to have a place where they can put in a pulley that's going to ride like on the inside of there for the string to go around. And this whole thing kind of captures it so the string can't pop off the pulley, at least not easily. I think if we look at the top ones, it might be a little bit easier. Yeah, here we go. So looking at the top ones, again, we have those places for them to be able to bolt this in. They actually have some cutouts possibly for the bolt heads from the other side or something, or just to make it a little bit easier to fit in. Oh, and then you can see kind of why that whole shape exists here, so that this bearing on the side has a place to ride. So they just use the same part on the bottom, even though it doesn't interfere with that bearing in the same way, because those bearings going the other way. They just use the same part, so it has that same kind of bearing cutout and everything down here. Okay, so yeah, so this string is tied up to the top, so probably in here actually. I think that's what this little box does. Let's see. Yeah, so this box I don't think can do anything else. So I think this box is what ties this string to be stationary here. So in real life, this is probably somehow rammed through this and then bolted in so the string can be fully clamped. And so then this part of the string basically has to stay stationary to this. And then the lower portion um, gets attached, I think, to here on the carriage. So I think this like ratchets around it. But yeah, you can see this. They have a ratcheting wrench here. And so as they spin this, they can kind of tighten up that string. So if they need to tension the string more, they can just tighten the spool. And so then this part of the string always stays attached to this part of the carriage. So then when the first stage of the elevator goes up and this pulley goes up, this part of the string stays attached to the ground surface, right? This is attached to the stationary stage, so it doesn't move. And so that means this part of the string has to get longer. So the portion between here and the pulley, you put more length of string there. That means the other half has to get shorter. And that was what actually raises the carriage up. So you're not able to raise the first stage without also raising the carriage the same amount. And you can kind of see that happening in the CAD. For every inch this first stage moves up, the carriage moves up an inch as well. And that's how you get the full motion of the elevator. And the last bit of the elevator we haven't talked about is this like upper structure here. This is always something we've had issues with in different times, is trying to figure out the best way to sort of tie the two elevator side plates together, either the stationary rails or the first stage. And so they do it pretty cleanly. So they have tube inset blocks in here. They just bolt this thick piece of aluminum. So this is a 1/4 inch thick aluminum. They just bolt into the top and then run around to the other one. And then so that stops these two beams from being able to like separate from each other or get closer to each other. And they basically do the same thing again on the inside, except because they're kind of using their inside space already for these pulley blocks that they have mounted here. They just went ahead and put the end caps on the inside and basically use them as like large nut strips so that they're able to bolt in from one side and then here bolt these in as well to give them that same loop around effect. Let me get us back to where we can be kind of in the right orientation on the robot. And that lets their arm and their pivot get really high, like all the way above or very close to above the top of their first stage. So that gives them a lot of height to be able to play with. So they can get the algae all the way up to the barge and they can score L4 super easily. Okay. I think that's most of the elevator. Oh, the last thing we didn't talk about is their cable management. And so for wiring on the elevator, they're just going to send the wires up this side tube, I think. Yeah, so you can see they kind of have like this little wire channels built here. So they build this whole like little tunnel. So that pushes off this polycarbonate plate so they can run all the wires they want up this side of the 2x1. They can run it over across here and they run it down into this what's normally called like energy chain. I guess makes a bunch of it in the kit of parts and things. And so then this just loops down and around, and then this is where the power wires for the arm and for the claw can both be run into there. And then I'm not sure if they run anything else up the elevator. That might be the only things. I don't see anything else, but they might run something else. If they have sensors or anything, any of those wires would also be run through there. And so that gives them a nice, easy place so that as this rises, you just kind of like the bottom of this U just gets higher and higher until it's right here and you end up with like the rest of the wires going straight up. So this is a really clean way to do that. And with the angled arm and everything, you don't run into those wires because the the arm gets further away from it by the time it's there. So if you had like a straight out arm, it'd be trickier because you'd run into the wires. But because they have the angle, they're able to have all the clearance for things like the ropes and the wires and anything like that. This whole side guard, all of that can be in there without interfering with the arm rotation. Okay, let's move on. We got about 15-ish minutes left into the carriage. So the carriage itself is built on these two 2x1s and the plates around it. And so you're just getting these 1/4-inch plates, probably, yeah, 1/4-inch plates, riveted or bolted into these 2x1s, and then just the normal West Coast Products bearing blocks here for the carriage to ride up and down. Oh, I didn't mention earlier, but the bottom end of this spring or of the string. So I think what's happening, we talked about it being ratcheted into here. So the string is probably cut. This is ratcheted to provide tension. Then the lower segment is mounted to the spring, and that helps take up any slack that's created or any dynamic slack if you pull on the string too hard or any stretch or anything like that. This spring can help alleviate, can help remedy that. And so the same thing happens on continuous string elevators too. A lot of times you'll have a spring here, just because there's always some amount of stretch, and just as things are moving quickly and things, you can get some amount of slack in the string, and the spring helps solve that. Okay, back to the carriage. So the way the carriage works is you have this really big circle in here. And so that is actually sandwiching a large bearing. Is that the large bearing? I think that's the large bearing. Let's see. I think I clicked on it. Yeah, so that's the large bearing. So this, although it looks like some sort of polygon, this is a circle. So this is basically a really large bearing, the same type of bearing that we use on like the swerve modules, except even bigger. So I think this is like a, what is that, a 6-inch diameter? So yeah, so instead of like a 4-inch diameter that we use on the swerves, or 3.5, whatever's on, depending on the swerve module, this is a 6-inch diameter X contact bearing. And so it's designed to take loads, both like up and down, and some of this like left, right, and everything. So it's pretty, it's constrained well. And so it only has that one bearing, I believe. I don't think there's anything in the back. Is there a bearing? Oh no, there is a bearing in the back. Oop, that's not the wrong button. What did I do? All right, there we go. Let's try that again. All right. Yeah, so there is a second bearing back here as well. And so they end up basically clamping the inside of the bearing. So you can see the bolt head here sort of clamps the bearing and doesn't let this be able to pull through it. And the same thing kind of happens to not let the bearing go out the other way. And so this whole thing can rotate the inner race of those two bearings, but the outer race is held in by that piece of sheet metal that I just hid. So you have this little piece of sheet metal, and that holds in the outer race of the bearing and kind of keeps it all stationary with the bigger stationary plate. And so they're just rotating that inner piece of the bearing the same way like the inside of the hex bearing or something like that spins. That's all basically the same. They have another one of those plates here. So they didn't do any 3D manufacturing or anything. This plate itself is all just 2D. So you could just either laser cut, water jet, outsource, FabWorks, however you want to do it. So all of this could be cut out and just very lightened geometry to keep everything relatively lightweight. And then they just add in those thinner sheets to, the sheets of 16th to actually hold the bearings in place and not let them slide in and out. Let's see. In addition to that, so they're clamping those whole bearings, and then they have the actual main driving force is this very large custom gear. So again, it's that 10 teeth DP gear, except this is a full 360, so it's not the sector gear, it's just a very large gear that has the full lightning pattern. And then like the mounting holes they need to actually be able to mount the arm are all built into that. They do that just with a little bit of nut strip and some plates and tube to get the angle of the arm that they needed. And then the last part that I want to go over, I guess we didn't talk about the gearbox. We can do that really fast. Again, these are all pretty normal at this point. So you just have the Kraken. They have some internal gears here, or just at least an internal gear. So you'd have a pinion here that doesn't seem to be catted or is hidden for some reason, up to a gear. And then that shaft is driving your 10DP pinion. That's then driving the really large arm gear. Looking at this, it doesn't look like they have an absolute encoder anywhere on this. This middle thing here is what's called a slip ring. And so this allows you to have continuous power through like continuous rotation without worrying about like the wires getting twisted or disconnected or anything. So it basically lets you have 6 wires get plugged in to the back of this. So in this case, I think they're running at least 2 for power and 2 for CAN. And then on the other side, you get these 6 outputs that are all able to basically spin freely around on the inside. So this kind of works the same way like a brushed motor works, or at least most of them do. And so they have little rings and brushes that go around and contact them. You can make slip rings a whole variety of ways. I haven't actually opened up one of these. I think these are the ones that Andy Mark sells. But you can make them in a variety of ways. There's some that use like mercury, which aren't legal because then you could end up spilling mercury on the field, which is bad. But there are quite a few legal ways to have slip rings that do work, and as long as they're rated for the current and everything that you need, they're a good way to do continuous rotation. If you only want a little bit of rotation, you can just have enough wire there that the twist is okay. Or you could potentially mechanically pass it through like we did for Photon, where we just like passed the intake shaft through and then ran a belt out to the front. So we didn't have to spin the motor at all. So there's a lot of different ways you can solve the same problem. A slip ring is just one of them. Coming out to the rest of the arm, I think that's about where we'll finish up. Relatively simple. A lot of robots had a very similar concept out here. So this is just 2x1 aluminum tube with all the holes in it. They have a nice, simple mounting plate for the motor off to the side and a belt out to the claw. And so that belt comes in and is driving this sort of large pulley. These are all going to be 3D printed. And so you can do a lot of custom attached stuff here pretty easily. So you can have the belt that's pulling from the main motor. You can have a large gear reduction here, and then you can have another small pulley up here to go to the one side of your claw. So they're getting a belt reduction here and another one here for this side. And then on this side, because they need to get the reversing, they have a gear reduction and then they have the pulley reduction. So you get 2 pulley reductions and then a gear and a pulley reduction. And these are likely spinning at either the exact same speed or very close. We could count gear teeth or look at the model and stuff and figure out exactly what this gear ratio is compared to this one. But my guess is they're pretty close to the same. They look about the same. And so you can see they used really big gear teeth here since these are printed. They went ahead and made these at least 10 dp. They could have been something else, but they're larger than 20 dp. And they have a really tall face width. So they have a lot of room here to play with. So they just made these teeth really tall. And so that again helps you not worry about your teeth breaking just because there's a lot more material transferring that energy. And so you don't have to worry about them breaking nearly as much if you just have big gear teeth. If you're going to have something that's printed, the smaller your gear teeth are, the stronger your material needs to be for the same load. And so that's why we end up using steel and things for small gears. But if we're printing something, we want as big of gears and as big of gear teeth as we can get. Okay, so yeah, so this is what brings in the coral. They have a couple of 3D printed stoppers here to kind of center the coral, make sure it doesn't come in at too much of an angle. Then these are just polycarbonate plates, it looks like. There's some amount of pocketing going on here, so it looks like they were able to, like, on their router, they sort of pocketed the plates to cut down weight a little bit. If we're doing this is probably just max composite for us so that it's just impact resistant. We're not worried about it breaking, and we can just get it off the laser cutter pretty quickly. Pretty normal sort of double wheeled intake that teams used in plenty of different games. We just have the shafts here. This is 2018, things like that. A lot of teams use the same kind of setup where you just have your plates and then you have your cantilevered wheels on each side of them. Nothing too crazy. Oh, they do have a sensor here to know that they have the coral. So that's going to be fed back through that slip ring. As a couple more wires, I believe. I don't think there's any way that they're putting it into the Kraken or anything. It doesn't look like they have any of that stuff going on. What else? I think that's most of this robot. Oh, we didn't see this exact crossbar, so they have that same sort of 3D printed setup here. Again, they have some bolts in there to reinforce it, which is definitely a cool way to do that to make your 3D prints a little stronger. Little printed RSL light mount here on that crossbeam. And then this crossbeam goes all the way from the one corner of their robot all the way up to the other corner of their elevator, helping to stabilize that whole setup. So that's a nice, it breaks symmetry a little bit, but it's definitely stiffer. So that's a nice, clean way to do that if they don't need the room for anything else up there. And then I'm not sure what some of those other things are. So they got some loops and stuff going on that may be used for who knows what. Some other attachment things just to make sure stuff isn't moving around too much, I imagine, or maybe they needed to run wires or whatever else needed to happen on the real robot to make that work. Okay. I think that's most everything else. Yeah, they have various limelight mounts, all 3D printed. Is there anything else we missed here? Don't think so. Battery case looks partially 3D printed. Yeah, a couple different bars there. Yeah, sides and everything. Some way to get a strap in, I imagine. Yeah, the little plate here gives them a little place to cut out for their for the motor to go through. So when the arm needs to come all the way down to actually grab algae off the floor, they made this nice little cute cutout for the motor to go through, and then this part here for the arm to actually kind of sit on. So as everything comes down, they make sure that it's not hitting the belt or anything. I imagine there's some way that it doesn't quite come down as low for that to hit or anything in real life. So it seemed like they gave that whole plate enough room for the arm to sit where it needs to. Similarly, some more 3D printed stuff to kind of hold everything and set everything exactly at the right spot for what they needed. All pretty good, using the ability for 3D prints just to have whatever geometry you want. And then in other places using the routed aluminum and things to their strengths where they need to various places, stiffening up the elevator mounts, things like that. All right, that wraps it up for us tonight.